Newton's cradle is an example of conservation of momentum or momentum transfer in collisions. It's a set of 5 identical balls suspended by a string, and we begin by giving the first ball an initial velocity, not a velocity, but a height above that surface. When we release it, it has some velocity, and because it has mass, it has momentum. Upon collision, that momentum is transferred to each individual ball, and we can see what happens. With each collision, the momentum transferred to the next ball and to the next and to the next and to the next until it reaches the end, where the final ball comes out with approximately the same momentum that the first one had coming in. But if we pull 2 balls to the side, we have twice the momentum, at least, so we should see a different effect. And those 2 balls continue to kick out too. And if we pulled 3 balls to the side and increase this momentum, then that would need to have 3 times the momentum. And so it's got to make a decision about this middle ball here, because we can't violate the law of conservation of momentum. Now eventually, if we let this go long enough, we'll see that the entire system will come to rest. And you might have noticed in the video that every time there's a collision, you hear things making sound, and we have a little loss of energy due to the friction that shows up in each collision. And so ultimately, we end up losing all of our energy to sound and heat. But here we're talking about conservation of momentum and the role that that plays in the different types of collisions. So let's take a look at the 2 different types of collisions that we'll be experimenting with in our study of momentum. So if this system were truly a closed system, we would see that the total momentum of the system before and after every collision would remain constant. And we could represent that by mass 1 times velocity 1 for the first ball, and then mass 2 times velocity 2 to the next ball. And then in the end, we would have mass 1 times velocity 1 prime, which tells us that that final velocity is different than this starting velocity. And then plus mass 2 times v2 prime, which once again distinguishes between the initial velocity and the final velocity. The law of conservation of momentum says that the total momentum of the system before the collision and the total momentum of the system after the collision will always be the same. And this would be the general law of conservation of momentum. It holds true for each system type that we have. Now, suppose that I take this basketball, which has more mass, we could say, than this tennis ball, and I drop both the basketball and the tennis ball from the same height. Well, if I release them at the same height, they should land on the floor with the same velocity. So though their velocities would be the same, because the basketball has more mass, it's going to have a larger momentum upon hitting the floor. So we can see that if we release these from the same height, even at the same time, and they even bounce up to about the same height, which means that this ball doesn't have a whole lot of air in it, but that's okay. For our point is that we can see that the reason it doesn't come back up, which we've talked about in terms of conservation of energy, to the same height that it was released from, is because it gives some of the energy away. But the momentum that it is giving to the floor is what we're looking at. And so what I want to do is, I want to actually combine these 2 balls. What if I were to take this tennis ball and stack it on top of the basketball? Earlier when we saw the tennis ball only bounced up to about this high. But if we stacked it on top of the basketball and we dropped these 2, then we would see something different perhaps. And here we can see that the tennis ball took off to a much greater velocity. How did that happen? Well, kind of similar to Newton's cradles, we had a momentum transfer in this collision. And so when the 2 balls came in contact with the floor, the basketball, as it rebounded back up, came in collision with the tennis ball that was still kind of headed downward, and it passed the momentum of the basketball back to the tennis ball. So then the tennis ball has its momentum plus the momentum of the basketball, and then you can see that certainly the mass didn't change, but boy, the velocity sure did. In physics, we're going to typically deal with 2 types of collisions. we're call these elastic collisions and inelastic collisions. Elastic collisions are where we have objects that will collide and come apart. Remember that when we're talking about momentum being a vector, the direction that something is going is very important. So it could have a positive momentum or a negative momentum. But in an elastic collision, we typically start off with two objects, they collide, and they bounce apart, so to speak. Think elastic is bouncing. The other type of collision is an inelastic collision. And this is where I might start off with two things apart, but when they collide, they stick together and they move with a common velocity. Remember that equations don't work just one direction. We could start over to the right and work our way back to the left, and that is true of the inelastic collisions too. Things could start together and then end up apart. But still, in both cases, the total momentum before the collision and the total momentum after the collision will always be the same in a closed system. So we have two equations to describe these collisions, and we will be doing labs with investigating with both types of relationships with our air track and the momentum that transfer that happens in a couple of different ways. So we'll spend a day on elastic collisions and we'll spend another day on inelastic collisions. But in both cases, it's still always very important for us to understand that the total momentum before the collision and the total momentum after the collision are the same. This little toy, they call this an Astro Blaster. So certainly we have 4 bouncy balls, and they're held together kind of by this stick, but the top ball here, you can see, well, each of these balls are separated from the other ball. The top ball can come off. And you know, with a bouncy ball, you take a bouncy ball and you drop it, it comes back up to a pretty nice height. It doesn't come back to the same height because, once again, conservation of energy gives some energy away to the floor. But what happens when we release the Astro Blaster from a height and we see, kind of similarly to the tennis ball and the basketball, the bottom ball is quite a bit more massive than the top ball. And so even if I release this from a very low height, even if I just release this from about a foot off the floor, you can see, oh, that was not so great. Let's try that again. But even if I release this from about a foot off the floor, you should be able to see that the momentum transfer is significant.